So last time we looked at graphing quadratics that were given or easily put into factorized form. But as we know, some quadratics like this one aren't as easy to factorize, but back when we were solving equations, we actually developed a formula that we could use to still easily solve for y being equal to 0. Now we won't go through the details of that again, but remember y being 0 meant we were looking for points on the parabola that were on the x-axis. So the moment we put y equals 0 and solve that equation, we're actually hunting for x-intercepts. Okay, those points where the parabola hits the x-axis. So we're going to go straight for the formula at this point, which you'll see on the side here if you need a reminder. We have the negative b, which would be positive 4 up first. And then inside the root, we have the square of b, so the square of negative 4. Then it's minus 4ac, where we have a being 2, and c being negative 1. The bottom is just 2 times a, so again, the 2 drops down there. Now inside the root, it turns out to be 24. And the bottom is of course just 4. The root 24 can now split into root 4 and root 6, okay, but the square root of 4 is of course a regular 2, so we get 2 root 6. And finally we simplify by halving everything. And hopefully that's a familiar process to you from solving equations not too long ago. So those are our two x-intercepts, 2 plus or minus root 6 over 2. And that corresponds to these 2 points here. So if you weren't sure whereabouts they were, you could always use a calculator to see sort of where to place them, whether they're positive or negative or whatever. But for now, let's look at these two answers a little more closely. The first ingredient here is this 2 over 2 part. Okay, and yeah, it's 1, but the important thing here is that it must be right in the middle, right between the two x-intercepts. Why? Because when you look at the next ingredient in the formula, that's the plus or minus stuff. So it only makes sense that on the graph, that would correspond to moving some equal pink distance either way from that middle green point. And so that's why that first ingredient, the 2 over 2 part before the plus or minus sign, must always be halfway between the two x-intercepts. And by the symmetry of the parabola, that must be the x value of the vertex, the turning point of the parabola. And so the vertex can be found when x equals 2 over 2, which of course, as we said, is just 1. Okay, and so how do we know then where exactly this vertex is? Well, we need a y value. Okay, and to get a y value from an x value, we can just put it into the original equation. So we put the original equation here, but in place of the x's, we will push in the 1's, and we get negative 3. Okay, so we know the vertex here has to now move down by 3, so all the way down to y equals negative 3, and then we can draw the parabola passing through all those points we found. To be polite, we can also quickly work out the y-intercepts, but remember that's when we just put x equals 0 into the original equation. And so if we look back at the original equation up the top right corner here, the moment we put x equals 0, those two first terms both vanish. And we're left only with the negative 1 at the end. Okay, so hopefully it's obvious that this will always happen. The number at the end that's not carrying the x will always be the y-intercept. Okay, and in our case, it is this negative 1. And where possible, we do label the x-intercepts, but sometimes if they're a bit complicated like this, we just make sure they are very clearly written somewhere. Okay. It's often nice, of course, to label the vertex too, so the 1, negative 3 we found earlier. And once we have all that information there, we are done. Okay, and that's how we can use the formula to draw graphs. But along the way, we've also, I think, picked up a sort of visual meaning to each piece of the formula, which is just as important, I think. Okay, so let's summarize this into a general approach. Given any quadratic, y equals ax squared plus bx plus c, it's easiest to start by thinking about putting y equals 0. That gives us a familiar quadratic equation we can solve. We try factorizing it if it's easy, but if not, we have this formula that solves it for us immediately. Now remember, the significance of this though is that we put y equals 0 into the original equation, which on a graph translates to locating the x-intercepts, where the parabola hits the x-axis. We then saw, by considering the symmetry of the parabola, that the vertex can be found when the x value is exactly this first ingredient here. So it would always be at negative b over 2a, and that's because that x value must be the point halfway between the two x-intercepts, from which you would plus or minus the stuff inside the root. Now the cool thing is this negative b over 2a thing works even when there are no x-intercepts, and I'll show you a bit of a visual of that in the next example. Alright, we can then work out the exact location of the vertex by putting this value of x into the original equation to work out the y value. Okay, and if we're also interested in the y-intercepts, we can find that one quite easily by just putting x equals 0. Back on the original equation up top, with c, all that does is it just kills the first two terms, and we are left with just the c. So c, the number at the end, must always be the y-intercept. So this might be a good screen to pause and write down if you want to take notes. Okay, so final example here, let's take this one. I just want to illustrate what happens when there are no x-intercepts, and so we won't put as much detail into the calculations. It's really all the same as the first example in that regard. But we'll pretend we don't know this. We'll try and solve for y equals 0 in search for x-intercepts anyway. When we use the formula though and simplify everything, we find that the guy living inside the square root is negative, and so that means we have no real solutions, which corresponds to there being no x-intercepts for this parabola. But notice I said no real solutions, because there still are solutions, they just live in the complex space surrounding the x-axis, and so we can still dissect these two values of x into the two separate ingredients in a meaningful way. We do this by sort of cheating. We peek into the complex plane, and we can now interpret the pink part as pushing us equally far into the complex plane in two opposing directions. But the important thing is that halfway between these two destinations still sits a perfectly real number, and of course it's just the number 1, the first ingredient in the solutions we got from the quadratic formula. And so now pulling it back to the real world only, we find that the vertex can still be found at that first ingredient, at that green number, okay? Which, again, for us is at x equals 1, sorry for the coincidence there. But to find the y value from there, we just need to put it into the original equation, and that gives us negative 2. So the vertex actually lives down here. Now, which way would we draw our parabola? Knowing it's a negative x square is enough to tell you it's a sad face. But the other reason it's a sad face is that that's the only way to avoid any x-intercepts. If it curves up at all, it's going to smack into the x-axis. So we can just draw something like this. We can confirm the location of the y-intercepts by just looking at the constant number at the end, which for us here is negative 3. So we can label that there, label our vertex, and we are finished. Okay, and so that's all for this one. That's how we draw parabolas that we can't easily factorize by using the quadratic formula. So thanks for watching, see you around.